So we have a parabolic path where the skier is going down, right? And this is the ski track, right? And we are given the equation y is equals 1/20 of x squared. We are given the velocity, the instant velocity at that point, 6 meters over second, and we are given the rate of increase of that speed, which is 2 meters over second squared. And we are being asked to find the direction of the velocity and the direction and the magnitude of the acceleration. So what do we do? Let's find first the velocity. So we know that the velocity as a vector is the magnitude of the velocity times the direction. What is the direction of the velocity? We know that the velocity is tangent to the trajectory. So we can draw our tangent vector. So we know that our velocity is always tangent to the trajectory, and we have a normal vector as well. And we actually are given the magnitude. The magnitude is 6 meters over second. So what we need to find is the direction. How do we find the direction? Well, we know that since it's tangent to that trajectory, and we are given the equation of that curve, where we know that the slope or the tangent of that equation is just the derivative. So the tangent will be the derivative of that expression. If we derive that expression, we'll give 2x over 20, which is x over 10. And we know that x, for that point A, x is equals to 10 meters. So for 10, x equals 10, we get that the y over x is equals 10 over 10, that is 1. Which angle give us a derivative or tangent that is, the tangent is 1? We know that that angle is 45 degrees. So we know that that's the tangent of the angle, and to get the tangent of the angle to be 1, we know that is 45 degrees. So the answer to the direction of the velocity is that we have a velocity of 6 in the direction t meters over second at 45 degrees. And then get that as a vector. So that's the answer to the first question. Let's work now with the acceleration. Since we have a curved path, we know that our acceleration has two components. One in tangent direction, and one in normal direction, right? And we know that the tangent is the rate of change of speed, and the normal is the velocity squared over the radius of curvature in the normal direction. And we actually are given that one. Rate of change is of speed is 2, so actually that is easy. We have that this is 2 plus the velocity is given 6 over radius of curvature. So what are we missing in this equation? And we have to write our units, right? Meters over second. So the only thing that we are missing is the radius of curvature to be able to find our acceleration. So that's the point of this example, to illustrate how to calculate the radius of curvature when we are given the equation of our path. So the radius of curvature is given by the expression 1 plus, the first derivative to the square 3/2 over the second derivative dx. I don't expect you to learn this expression by heart, or you will have some formula sheet. Having the formula not always gives you to the answer. You need to know how to use it, right? So once you have the formula, you need to understand what you have to do. Well, we already have the expression for, we know that dy over dx, we already calculated, is 1x over 10. And then the second derivative is very easy because it's a polynomial, right? So the second derivative will be 1 over 10. And if we plug these numbers over here, and will be 1 plus, we actually need to evaluate that in x equals 10, because we are finding that radius of curvature right in for that point, and x is equal to 10 again. So actually we have 1 square, right, over, and this is 2 3/3, and this is 1 over 10. And that, well, I have the result here, right, in this 28.28 meters. So this is our radius of curvature that we will plug in here to find the only unknown that we have left to be able to find our acceleration. So our acceleration, normal component, which is the velocity, over 28. That is equals to 1.273 meters over second square. So finally, we can write our acceleration as a vector, 2 tangential plus 1.273 in the normal direction, meters over second square. So that will give us the acceleration as a vector, the acceleration as a magnitude, as we know, is the square root of every component to the square, and that is equals to 2.37 meters over second square. And actually what we are left to find is the direction. So let me get myself a little bit of space right here. So the direction of acceleration. So we know that we have a normal component and a tangent component, right? So we have this is 2, and this is 1/3. So our angle that we can find is between these two, right? So I can find this angle P, that will be a resultant. Phi will be this angle. Phi will be tangent to the -1 of the tangential component, which is 2 over 1.273. And that angle gives me a value of 57.3 degrees. So that angle, let me write that phi better so you got it right here. This is phi, which is this phi right here. Okay, so we found, so our acceleration is something like that, and we found that phi. If we want to find that angle in terms of x and y, we found already that this angle is 45 degrees, right? So, and we know that this is tangent, so between these two is 90 degrees. And this one we just found that is 57 degrees. So the whole angle, this whole thing will be 45 plus 90 plus 57.3. That angle gives me an angle bigger, so that angle is like about here. So that gives me an angle bigger than 180. If I want to find this tiny angle, so to find it from the horizontal, I will subtract 180, right? Minus 180 degrees. So, and that gives me, let's call that angle theta. And theta gives me an angle of 12.5 degrees. What is the angle of 12.5 degrees? So, from horizontal. So at the end, I have acceleration, the magnitude is equals 2.37 meters over second square at one angle of 12.5 degrees.